Hi everyone, Jamie here. Welcome to Read Papers with me. I have to read papers, you have to read papers, so let's read them together. Here are the rules. 1. We skip the abstract, related work, and experiment details. Instead, we focus on the study's motivations, model design, and experimental setup for verifying effectiveness. 2. This is not a summary, so there will be no commentaries. Let's get started. Today's paper is Proxy-based item representation for attribute and context-aware recommendation, presented at WSDM 2024 by me. Yes, since this is the first video, I brought my own paper. Alright, let's dive into the paper. Section Introduction. Recommender systems have evolved from collaborative filtering to machine learning and deep learning based models. In model-based CF, users and items are represented as latent vectors via learnable embedding matrix, which is implemented as a full lookup table, where each row corresponds to a unique user or item vector. Such vector representation approach can transform the recommendation problem into a set of vector arithmetic, assuming that the latent vectors are well trained through the training data distribution. To train the representations effectively and achieve higher recommendation performance, recent studies have introduced deep learning-based models and sequential recommendation models, as well as attribute and context-aware models. The concept of item embedding metrics also appears in the natural language processing field to train the distributional semantics of words. However, in contrast to the data distributions in NLP, recommendation datasets exhibit distinct and unique characteristics, which incur two significant limitations that need to be addressed. Firstly, the item frequency in recommendation datasets follows a long-tail distribution. The item embedding matrix, which is unaware of such data distribution, cannot accurately reflect the proper training signals for the infrequent items, leading to degraded recommendation performance. Secondly, the number of items may increase indefinitely. For a real-world recommendation scenario, a large set of new items is consistently added to the system, and the item embedding matrix, where most of the model parameters are stored, must scale up accordingly to accommodate them. For these problems being the case, it is necessary to devise a new methodology that can effectively replace the item embedding matrix and resolve such limitations. We further investigate the problem of infrequent item embeddings thoroughly. First of all, during the training process of recommendation model, items appear in three different scenarios. A user profile that is represented as the list of interacted items, a target item for the system to predict, and a set of negative items that the user has not interacted obtained via negative sampling. It is evident that the parameter update for a specific item embedding, except for that of negative sampled items, is directly proportional to the item's occurrence frequency. Consequently, infrequent items do not receive as many training opportunities as frequent items do, and thus their embeddings hardly converge to their optimal states throughout the training. We have conducted an empirical analysis of such phenomena under attribute and context-aware settings. Specifically, we have replaced a portion of infrequent items with a shared unknown token and measured the model performance. In Table 1, the right side, when the infrequent items are replaced by the unknown token, which can be seen as a removal process, the recommendation accuracy in terms of NDCG at 10 increases. Such result clearly demonstrates that the poorly learned infrequent item embeddings harm the overall performance, as mentioned earlier. However, such improvement comes at the cost of losing global coverage of recommended items, which accounts for item diversity, and highlights that the insufficient training signals for infrequent items need to be addressed.